All right, today is Wednesday, October 16th, and we have a very special guest excited to talk to Max Derakshani, who is in New York or somewhere,
Yes,
I
New
think. Is that
York
right?
and the
Okay.
Manhattan area.
All right, great. Max has been on Tom's podcast maybe more than anybody.
Only a couple of times. I don't know if that's
Three
the record.
times? How many times?
Twice.
Oh,
Just
oh,
twice.
so
Yeah.
okay. So you and I are in the two club.
Oh, okay. There we
Uh,
go.
I think somebody didn't you make a short one or a couple of short ones, or was that somebody else?
Um, I did two longish presentations, like
Okay.
45 minutes to an hour.
Right, okay. Yeah, there's somebody else who's done a bunch of short ones. So,
Mm.
all right. And do you have a presentation for us today?
I do have a presentation. Yes, it's essentially same topic about the El Nino Southern Oscillation and
Sure.
marshaling evidence that it is the strongest contributor to global warming insofar as that can be quantified.
Very exciting. We've gone back and forth recently about the tidal influence. Do you
Mhm.
include some of that, or should we discuss that at the end?
That I don't include because I don't have a strong view on that matter.
Huh.
Maybe not as much as you do.
No, Javier seems to. I'm just asking dumb questions and trying to learn everything. That's all.
Mhm. Well, that works too. But as
We'll
far as
we'll discuss it afterwards then.
sounds good.
All right, I think it makes sense for you to give your presentation, and then many of the students here are familiar with your work, and so I'm
Okay.
sure I will try not to monopolize all the question asking afterwards. But we are recording, so go right ahead.
Okay. I will share my screen now.
Sure.
Okay. I don't know. Asking for a. I will now expand this into the full mode.
It's we can see the whole thing.
You
So,
can see the whole
yeah,
thing?
looks good.
Okay. Okay. So this presentation is one that I've given also for the Tom Nelson podcast, and the aim of it is to compile evidence that there is a phenomenon of natural internal variability of the Earth's climate system that can explain global warming far better than, say, the rising concentration in atmospheric CO2. And none of this is going to be particularly original research to me, but rather an accumulation of different research studies that I've come across, that I've read over the years, and that struck me as offering a very compelling explanation of global warming through natural internal variability. So, ENSO is an acronym for El Nino Southern Oscillation, which, broadly speaking, is a phenomenon that couples ocean and atmosphere heat exchange, and it primarily occurs across the tropical Pacific Ocean. And there's a bit of history about the names, like El Nino translates to Christ's child and is the name of a Spanish fisherman. It's the name that Spanish fishermen gave to a periodic warming phenomena they observed in their ships, involving like ocean currents around the tropic, and it was usually observed right after Christmas time. And southern oscillation refers to changes in the sea level air pressure in the southern Pacific between two places, namely Tahiti and Darwin, Australia, which are both also in the tropics. And El Nino is the name is in a sense incomplete because it only refers to one part of this particular ocean atmosphere coupled phenomenon. So here's a visual of where Tahiti is in the tropics and where Darwin, Australia is located. And so the El Nino phenomenon occurs somewhere around here and involves the trade winds between Tahiti and Darwin. So during the El Nino period, um, what happens is that the average air pressure is higher in Darwin, Australia than in Tahiti. And when this is the case, it causes a change in the surface temperature of water in the Central and East Pacific Oceans. In particular, it results in warmer water surface temperatures. On the other hand, during the La Nina period, which is the other side of the oscillation phenomenon, the average air pressure becomes lower in Darwin than in Tahiti, and this induces cooler surface temperatures of water in that region of the ocean. So, in brief, El Nino refers to the warming period of the El Nino Southern Oscillation, whereas La Nina refers to the cooling period of the El Nino Southern Oscillation. And the periods in between, we say, are enso neutral. And these episodes of El Nino and La Nina typically, on average, last around 9 to 12 months. But durations can also vary, can be much shorter or even longer than that. So during the La Nina period, when the average air pressure is lower in Darwin, Australia than in Tahiti, what happens is that the trade winds, which blow from the east to the west across the tropical Pacific, get stronger than normal. And these stronger winds end up pushing more surface water to the western half of the Pacific basin, which results in pools of warm water growing deeper there and storing more excess heat at depths of the ocean. And this allows for colder, deeper water to rise to the surface in the eastern half of the Pacific basin. And so as a result, this creates a large region along the equator where the ocean surface temperatures are below normal. And over several months, the heat from the atmosphere flows into the ocean, which leads to cooler air temperatures over that Pacific Ocean region. And the magnitude, it turns out, is large enough to impact global average temperature anomaly measurements, as indicated by surface temperature measurements or satellite measurements. Here's a nice visual depiction of the La Nina period of the phenomenon in the Pacific Ocean, denoted by the blue region here. And that is going to be contrasted with the El Nino phase, which occurs when the average air pressure is higher in Darwin than in Tahiti, which results in trade winds that weaken or even reverse. When the trade winds weaken or reverse, the amount of cold water that migrates to the surface in the Eastern Pacific Basin reduces. And so warm waters in the West Pacific Ocean slosh to the east and create a large region around the equator where the ocean temperatures are above the average, so to speak. And so when the ocean temperatures are above normal, the heat from the ocean goes out into the cooler atmosphere above the ocean, which results in warmer air temperatures because the heat is transferred from the ocean surface to the atmosphere in that region in the Pacific. And the magnitude of that heat transfer is, it turns out, empirically large enough to again affect global average temperature and temperature anomaly measurements. And here is the corresponding image of the El Nino phenomenon, denoted by the red region here. So this is typically the magnitude of the, this is a way of illustrating the magnitude of the heat that is transferred to the atmosphere from the ocean during the El Nino phase as compared to the temperature changes in other parts of the oceans globally. And as you can see, it's quite large and crosses a substantial region of the Pacific Ocean and the oceans of the planet in general. So it's a fairly large heat source, or in the La Nina phase, a heat sink. So the key point here is that the ENSO, or El Nino Southern Oscillation phenomenon, shuffles heat from ocean to atmosphere and vice versa. Um, so the phases of the El Nino Southern Oscillation phenomenon don't necessarily create or remove energy from the climate system. It just transfers the energy content, the heat content, between these two portions of the planet. A colleague of ours at the CO2 Coalition, Ron Barnby, wrote a nice article about my presentation on this phenomenon a while back, and he analogized it to the ENSO phenomenon to a battery of sorts that stores a charge right in one place, and then it transfers the charge around to another place. So you might think of ENSO as something analogous to like an ocean atmospheric battery that exchanges heat between these two different places on the planet. So this is why climate scientists refer to ENSO as a form of internal climate variability, as opposed to what's called external climate variability, which would be, for example, the sunspot cycles from the sun, which affects the solar output, the solar radiation output of the sun, or perhaps other factors like changes in the orbit of planet Earth as a result of complicated gravitational dynamics in the solar system. So even though this is an example of internal climate variability, that is ENSO, even though it's just shuffling heat between the ocean and the atmosphere, it turns out that the El Nino portion causes a significant warming, enough that to show up on the global scale through global average temperature anomaly measurements. And likewise, La Ninas can produce global scale cooling, as indicated by those measurements. And the magnitudes of these coolings, or these warmings from the ENSO phenomena, are strongly correlated with the magnitudes of the ENSO phenomena themselves. And turns out that there are also multi-decade cycles of El Ninos and La Ninas, which is to say that the tropical Pacific Basin enters states where El Ninos are occurring much more frequently and with greater intensity over multiple decades. And there are periods where, multi-decade periods, where the tropical Pacific Basin achieves physical states that favor La Ninas for multiple decades as opposed to El Ninos. And it's not fully understood why that's the case, but it does seem to have something to do with the Pacific Decadal Oscillation, which is another ocean atmospheric cycle that I will briefly mention near the end of the talk. But in general, it's an open question why this is the case and why there might be irregularity in this process. So it's not exactly cyclical. The net heat output over any finite interval of time on the Earth, or the net heat exchange, is not the same. It varies considerably over multiple decades. Now, this is an example of how the El Nino Southern Oscillation is quantified. It's called the Multivariate ENSO Index, or MEI. And the MEI can be quantified on an annual basis, like the bottom chart shows here. and it can also be quantified in a cumulative sense. In this case, the data shows accumulation of ENSO, or the cumulative or annual multivariate ENSO index going back to the 1950s. And on the annual side, what you can see is that there are fluctuations in the magnitude in the MEI variable. When the MEI is positive, that indicates El Nino events. When the magnitude is negative, it indicates La Nina events. And you can maybe see just with your eye that on balance, between 59 and 76, there were slightly more and more intense La Ninas than El Ninos. So you can see there's perhaps a downward trend, which in fact the cumulative measure, that is summing the magnitudes over time, indicates. So on balance or overall, there were more and more dominant La Ninas and El Ninos, or net cooling, in other words, of the planet as a result of the ENSO phenomenon. But starting in 1974 or 76 or so, the balance shifted, and there were considerably more El Ninos than La Ninas and of much greater magnitude. And that's reflected also in the cumulative measure, which shows this significant rise in the cumulative variable. And then from 1998 or so until, in the case of this chart, till about 2015, the magnitude was about balanced, slightly more and more intense El Ninos than the La Ninas. So there's a very slight upward trend, but up to this point, it was more or less equal. And this is an indication of the multi-decadal aspect of the ENSO phenomenon. Okay, so this is another way of seeing the correspondence between the annual multivariate ENSO index, or the annual intensity of El Ninos and La Ninas, and how that relates to the cumulative variable. So again, you can see there are a lot more and a lot bigger blue bars between the 50s and the 70s, the mid 70s, and that corresponds again with the decline in the cumulative variable. And then from the mid 70s to 98, a lot more El Ninos, and that corresponds to the increase in the cumulative variable. And then about a balance of the two, which results in this relatively flat trend in the cumulative variable. And for those of you familiar with charts of global average temperature anomaly measurements, you might notice here that there is a sort of correspondence here, namely that this period of global cooling that was discussed in the 70s, or between the 50s and the 70s, it corresponds to this decline in the cumulative variable, or in the annual metric. And then from the mid to late 70s to about 98, when there was, according to those measures, some significant degree of global warming, it corresponds closely with this rise in the cumulative variable. And from 98 to 2015, if you're familiar with those data sets, the flatness of that curve is compatible with that trend in the temperature anomaly measurements globally. So the MEI is not the only way of quantifying the magnitude, or the frequency of the magnitude, I should say, of the ENSO phenomenon. There are many other measures like Southern Oscillation Index, Oceanic Nino Index. There are many other measures. At the end of this talk, I will point out what I think is an even more promising measure of the El Nino Southern Oscillation phenomenon, which is just a direct measure of the heat content of the tropical Pacific Ocean. But nonetheless, the MEI is one of the most comprehensive, one of the broadest measures that has been used in the past. So here is the NOAA, who explains who uses the MEI measure and explains what it's based on exactly. So as they say, the MEI, the multivariate Enzo index, is based on 6 variables, one of sea level pressure, of zonal and meridional components of surface wind, of sea surface temperature, of surface air temperature, and total cloudiness fraction of the sky. One can certainly criticize the comprehensiveness of this measure or the relevance of maybe certain factors like total cloudiness fraction of the sky. One could even critique the means by which they measure these quantities. They all come from something called the ICOADS database of ship and sea measurements. Nonetheless, what we can see is that it does include sea surface temperature and surface air temperature as part of the metric. So temperature plays a role here in a crucial way. So the MEI is at any point in time, it's a linear function of these 6 variables, all in the tropics. And so that is the measure that I'm going to use a bit later on in the talk to try to find a explanatory account of global warming in terms of the Enzo phenomenon. So the question is, could global warming be dominated by the Enzo phenomenon? Well, we've certainly seen as an empirical fact that El Niños lead to warming of air temperatures globally and that La Niñas cool globally. We've also seen as an empirical fact multi-decade cycles of Enzo that lead to net cooling, as from this period, 49 to 77, and also significant net warming from 77 to 98, and not much trend from 99 to 2015. I should also clarify that in the previous chart, the data ends right before the point of this super El Nino that happened between 2015 and 16. That's why there's not much trend. Of course, if you extend the data further, as more recent measures do, then you do see that there's a significant trend upward because of that super El Nino period that happened. So it's natural to ask the question, how strongly do global average temperature anomalies in the atmosphere correlate with the Enzo phases? And can Enzo explain most of the warming and cooling periods in the temperature anomaly records, of which there are many? So here's a nice comparative chart where I've taken the UAH, University of Alabama at Huntsville, satellite measurements of global average temperature anomaly in the lower troposphere, or the lower portion of the atmosphere. And this chart below it is the multivariate Enzo index version 2, so an updated version of the multivariate Enzo index. After 2018, NOAA discontinued the MEI and decided to use a new index called MEI version 2, which differs slightly in the way they measure certain quantities. And I've done a whole investigation as to why they changed the measure. They don't really give much of an explanation, except to say that, well, we use some different data for the MEI version 2, but they never give a justification as to why they think this is more accurate than the previous measure. Nonetheless, I like this chart because it, I think, does allow you to see a nice correlation between El Niños and La Niñas, at least qualitatively speaking. I'll speak more to precise magnitudes later on. But if we, yes,
So is
David.
this retroactively applied, the version 2, to the previous data, or is there a cutoff? Or
Well, it's retroactively applied, yes.
and,
Yeah, so that goes, they only started producing MEI version 2 in 2019. But they applied it back to 1979.
and you don't think there's any funny business behind that?
I actually do because I've spoken to the managers at NOAA who manage these data sets, and I've asked them, so what reasons can you give for why this is a more reliable measure of of El Ninos and La Ninas than the original MEI index? And they don't really say why. They just say, well, we just have a new data set where we can measure outgoing long wave radiation with satellites. And so we replace the measurements of sea surface temperature and air temperature with that quantity instead. And then I raised other questions about that, like, well, doesn't that outgoing long wave radiation measurement by satellites have problems insofar as it's confounded by other factors like maybe cloudiness of the sky and maybe cooling trends in the troposphere and in the upper troposphere and sorry, excuse me, stratospheric cooling
Oh,
trends, which are known to be observed. And they just say these are good questions. Here's someone else you should talk to about that, but no analysis has been given as to how the MEI index version 2 might be confounded by these factors. So it's a bit of a mess, in my opinion.
if we put those two, version 1 and version 2, up against each other, what would
Yeah,
be what would be the signal change?
that's an excellent question and right on the nose. If you do that, and you'll see it later on,
Oh,
I
okay. Well,
think,
so,
which I will,
yeah,
or at least you may pick up on it later on.
go ahead.
But in short, what you notice is that in the original MEI index, the magnitude and frequency of El Ninos is significantly greater, visibly greater than the magnitude and frequency of La Ninas. And the magnitude and frequency of La Ninas is significantly smaller in the original index.
Uh-huh.
So
Uh-huh.
there's still something to be assessed there. And at some point, I'd like to do a more thorough investigation and write that up, or perhaps talk about it in a future presentation.
Okay.
So yeah, so just in this chart, if we start at 1979, first we see an upward trend in the global average temperature anomaly measurements that is consistent with this little period of small El Ninos. And then we see a decline in the temperature trends, which is broadly consistent with this little period of La Ninas. And then we see another period of El Ninos, which is followed by a slight increase in global average temperature anomaly. And then again, a period of La Ninas here, which is broadly consistent with this decline in the temperature anomaly trends. And then again, period of El Ninos, which goes with this, is followed by this, with a slight delay, this period of increase in temperature anomaly measurements. And then once again, a decline followed by, which is preceded by this period of La Ninas. And then here you notice something interesting. Even though El Ninos are very, very small, and then they become very big and stay for quite a while, what you see is an increase in the temperature, and then you see a decline here, even in the period of the largest El Ninos. And then you see a trend in the temperature, and then it basically stays unchanged, even though you have this period of La Ninas. And it turns out that volcanic activity of the 80s can help account for this for reasons that I'll explain a bit later on. But what you see here is that there was the super El Nino in 1997-98, and that coincides with this big spike in the temperature anomaly record. And then this period of La Ninas, which corresponds with this drop again in the temperature anomaly record. And then you see this period again of a rise along with El Ninos, balanced by La Ninas. So this period is about relatively flat, and it's relatively flat in the temperature anomaly record. And then you get a dip in the temperature anomaly record, which corresponds to this dip in the MEI version 2, and then a rise again in the MEI, which corresponds to this rise. and then a decline, which corresponds to this decline. And then again, a big spike, which corresponds to this super El Nino in 2015-16. And then a decline corresponding to these El Ninos, a little rise again, and then a decline again. There's much more recent data for both, of course, the temperature record and the MEI version 2. And you see, again, broadly the same types of trends, except for the recent period of record high temperatures for reasons that we don't, I guess, fully understand yet, even when there are La Nina periods. And it might be, I should maybe add just to say, the multivariate ENSO index has recently also been discontinued by NOAA. So now they're using some of these other measures and indices, but for some reason they decided to discontinue it and have not explained why on the website.
I'm
Yes.
sure you got more. So I only want to ask, can you
Hmm?
give us an indication of what is considered neutral here?
Neutral would be the flat line here, 0. That would be the ENSO neutral case, or when, say, you have this very, very tiny little blip of an ENSO, of an El Nino, or this tiny blip of a La Nina. These are near ENSO neutral phases. So there's also noise in these measurements. And one question you might ask is, what are the error bars on these MEI measurements? And surprisingly, that has not really been addressed by the NOAA team that constructed this metric or the previous metric. So it's an open question and a fair question. Just how accurate are these measurements? Some of this might be within the noise of the uncertainty. So measurement uncertainties. But what we can see nonetheless in that chart, just qualitatively, is a clear correlation between the monthly variations in ENSO and on average around 6 months earlier to monthly variations in the temperature anomaly record, with the exceptions of certain major volcanic eruptions like Mount St. Helens in May 1980, or El Chicon in 1982, or Mount Pinatubo in 91, and Mount Hudson in 91. So if we go back to that chart, if we look at it, for example, a period of, say, 1980, there were a bunch of El Ninos here in 1980, but then around 1980, there was a decline in the temperature anomaly, even 6 months later or so. And then also in 1982 or so, there was a volcanic eruption. Even though, and at the same time, there was this huge super El Nino period. Yet it doesn't really show up in the temperature anomaly record, or it shows up as just this very, very small spike compared to, say, this one in 97, 98, or this one in 2015, 16, even though the super El Ninos were a bit smaller in magnitude. So why might this be the case? Oh, and also, I should say in 91 or so, we have this chunk of El Ninos, but the temperature anomaly record doesn't really reflect that during that period. In fact, you have a cooling from 91 to around 93. This is a cooling period, even though from 91 to 93, you had this big chunk of El Ninos. So why might volcanoes mask the effect of the warming effect of El Ninos? Well, it's because they release a lot of dust or particulate matter into the atmosphere, aerosols, in other words. And the aerosols presumably reflect sunlight back into space more than usual. And so, or they perhaps even seed more clouds, thick, low level clouds, which then reflect more sunlight back into space, or release heat into space through convection from the surface of the planet. And both of all these effects on balance would produce a net cooling effect. So volcanic eruptions, at least from the surface of the planet, can diminish or dampen the warming effect of El Niños. And I should say there were other large volcanic eruptions in the 2000s, like this Kale and Ha'epe in 2011 and 2022, but those both coincided with La Niñas. And it's conceivable perhaps that, well, I shouldn't say that they would amplify La Niñas, but they might amplify La Niñas, actually, that is a possibility. But they would also perhaps exaggerate the correlation between La Niñas and the cooling periods of the temperature anomaly record. So volcanoes do have to be taken into account when looking at these correlations between ENSO and the temperature anomaly record. Now, one of the first pieces of published research on this topic that I want to delve into is a paper in 2009 by McLean, Freitas, and Carter, which examines a particular measure of ENSO called the Southern Oscillation Index, and its influence or its correlation with tropospheric temperature as measured by the University of Alabama at Huntsville Temperature Anomaly Record, satellite record, and also the weather balloon temperature anomaly record known as RATPAC. So the Southern Oscillation Index differs from MEI and MEI version 2 insofar as it's based on sea level pressure differences between Tahiti and Darwin, Australia, and that's it. So it's a much simpler, more limited measure of the magnitude of the duration of El Niños and La Niñas. And here's what NOAA say about the SOI. They say that in general, smooth time series of the Southern Oscillation Index correspond very well with changes in ocean temperatures across the eastern tropical Pacific. So even NOAA says, yeah, this is a pretty good measure of the ENSO phenomenon and correlates well with ocean temperatures. So here's what they say in their abstract. The key point is that they find that the average global tropospheric temperature has, for the last 50 years in their analysis up to that point, fallen and risen in close accord with the Southern Oscillation Index of 5 to 7 months earlier, which shows the potential of natural forcing mechanisms to account for most of the temperature variation. And we can go through a longer detail, but I could read out the abstract in broader detail, but I'm going to explain its contents in the next slides. But maybe one thing that's worth pointing out is that for them, in their analysis, changes in the Southern Oscillation Index account for 72% of the variance in the temperature anomaly records in the troposphere for the 29-year-long satellite record and 68% of the variance in the weather balloon record. That's what they find. And they also find that the Southern Oscillation Index accounted for 81% of the variance in the tropospheric temperature anomalies over the tropics, which is where the El Nino Southern Oscillation phenomenon happens. So what they claim to find is quite, good evidence, I would say, of an explanatory relationship. So here again is a pair of charts from their paper. And on the top chart, they show the Southern Oscillation Index juxtaposed with the Global Average Temperature Anomaly Satellite Data Set, MSU. So the right-hand side, y-axis, refers to the Satellite Temperature Anomaly Index, and then the left-hand side, the Southern Oscillation Index. And it starts in 1980, ends in around 2008, according to their data set. And they also, what the black line here, as it relates to Southern Oscillation Index, is refers to the Southern Oscillation changes in the Southern Oscillation Index, but with a 7-month lag. So what they did is they found the 7th month prior Southern Oscillation Index changed, and then they put it on top of the satellite record for temperature anomaly changes, which is the light gray line. And so as you can see, from 1980, there's strong overlap, and then there's a divergence here in around 83 or 82 to 84, which coincides with the El Chican volcanic eruption. And then they come a bit back together, not greatly, but there's still a bit of divergence, but they come back together more and more throughout the 90s, throughout the 80s. And then around the early 90s and around 91, when Mount Pinatubo erupted, they diverge again and then come back together again in the mid 90s. Although there was another volcanic eruption around that period, a much smaller one, which might explain this little divergence. But they come back again throughout the 90s, matching quite closely throughout the rest of that period. And to complement that data set, they also look at the weather balloon uh, measurements of global average temperature anomaly in the troposphere, dating back to the 1950s or so, around 1958 to 1980. So essentially, before the satellite record began in 1979 or so, there were weather balloons orbiting the lower atmosphere, and they were taking measurements of temperature anomalies in the lower atmosphere. And so there's a record of this that goes back to the late 50s. There's some question as to how complete it is or not. Nonetheless, to the extent that data exists, they compare it also to measures of Southern Oscillation Index changes. And what they find again is very, very good agreement, except for periods here when there were volcanic eruptions called Agong and Awu. But then again, they come back and align rather closely during that period. So that is that data set by McLean and colleagues, showing, I think, some good evidence of a causal relationship, definitely a strong correlational relationship, and probably a causal relationship between global warming and ENSO. Now, what about ENSO impacts accounting for long-term temperature trends? So Dr. Roy Spencer, who's one of the producers of the UAH satellite record, along with Dr. John Christie, wrote this very nice blog post in 2019 called Half of 21st Century Warming Due to El Nino. And he shows that two measures of global average temperature anomaly, the UAH and the HAD Crude 4 surface temperature data set for the 21st century, can be entirely accounted for by the El Nino Southern Oscillation phenomenon. Why? Because by simply removing the big El Nino event in 2015 and 16, the result is that the UAH temperature trend for that period, 2000 to 2018, drops from plus 0.12 Celsius per decade to a trend of just 0.01 Celsius per decade. Or so rather, I should say that from 2000 to 2018, the trend is 0.12 Celsius per decade. And by just restricting to 2000 to June 2015, that is just before the super El Nino of that period that follows, the trend goes to nearly zero. And the RSS satellite record, which is another satellite record that competes with UAH, it halves to only 0.10 Celsius per decade. Likewise, had crude 4 drops from 0.16 Celsius per decade to 0.10 Celsius per decade over that same span, which suggests considerable evidence of a causal impact. And here is a nice visual depiction that Dr. Spencer produced on his blog. The top is 21st century global temperature trends from 2000 to 2018, involving the UAH satellite data set. That's the purple line, as compared with the Had Crude 4 surface temperature data set. That's the green line. And then all of this is compared with predictions from the UN's CMIP-5 climate computer models. That is the trends that they essentially predict for this entire period, the average trend that they predict for that period. So what you can see is that over this period, 2000 to 2018, there's an upward trend for both UAH and Had Crude 4. Again, of plus 12 for UAH, plus 0.16 for Had Crude 4. And this is consistent with the fact that the multivariate ENSO index from 2000 to 2018 shows the upward trend, and cumulatively shows an upward trend, clearly. And here again, you can see the correlation between the big El Nino in 2015-16 and then this spike in the temperature record. And you can see trends elsewhere in this. In fact, it aligns quite closely. If you gradually follow the black line of multivariate ENSO index as compared to the temperature trends of both records, there's quite good agreement between both, just visually, offhand. So this is what the chart looks like when you restrict the data set to just 2000 to 2015 and a half or so, or mid 2015. So here again, the temperature trend for UAH and Had Crude drastically decline, and correspondingly, the multivariate ENSO index for this period of 2000 to mid 2015 is virtually flat, or the net impact, the cumulative impact is net zero effectively over that period. Again, providing strong evidence of a causal relationship. So yeah, Spencer's findings suggest that global warming trends in the lower troposphere are due almost entirely to overall warming impacts of ENSO. But now the question is, does this finding hold up over the complete record of the University of Alabama Huntsville satellite dataset? And what about other temperature datasets? So fortunately, these questions were thoroughly addressed in a beautiful report by Wallace, Christie, and DeLeo called "On the Existence of a Tropical Hotspot and the Validity of EPA's CO2 Endangerment Findings." And this report, the way they approach this question is they use standard econometric modeling, in particular multivariate regression analysis of 13 different temperature data sets, 9 in the tropics, 1 for the United States, temperature anomaly trends, and 3 global data sets. And what they ask is the following question: does adjusting a temperature time series only for the impact of ENSO, for example, via the annual average MEI, cumulative MEI, and the 1977 Pacific shift in the MEI variable, that is the shift between mostly La Niñas to mostly El Niños, account for all of the positive and statistically significant warming trend in the data set, in the time series? And what they find in their report is that in each of the 13 cases of temperature time series analyzed, 9 tropics, 1 for the US, 3 global, they find that the answer is yes. Now, I want to look at 2 striking examples. Recall that this chart below is the annual average MEI metric, and the top is the cumulative MEI metric, and that they agree with each other quite well. Now, this is the report's analysis of the global tropospheric, lower tropospheric temperature anomaly data, average between the two satellite data sets of UAH and RSS. And what they do is they construct a regression model, a multivariate regression model involving the MEI variable that includes three of these variant factors: annual MEI, cumulative MEI, and this Pacific shift. And this econometric model predicts a global average temperature trend that looks like the red line here. And notice that it strongly overlaps, completely overlaps with the temperature trend due to the average of the two satellite data sets in the lower troposphere. That is the blue line. They both are going up slightly over that period. And they confirm that when they essentially subtract out the upward trend of the MEI model from the actual satellite data, they just get a flat line for the temperature trend. So in other words, the portion of the upward trend of the satellite temperature data set that could be attributed to global warming due to ENSO is pretty much complete over this period from 1979 to 2015. It completely accounts for all of the temperature trend. And here they do the same thing for the surface temperature data set of HAD-CRUD4 versus their MEI-based model fit. The MEI model is the red line, which closely tracks the blue line, which is the surface temperature data set. And again, subtracting out the model prediction from the actual data set, they get, again, a flat trend. And so, yeah, these are just two highlights of that report. They do many, 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 many other analyses, and in every single case, they find the same outcome. Okay, so I mentioned earlier that there are multiple different measures of the ENSO phenomenon, many different ways to quantify the magnitude and the frequency of El Niños and La Niñas. One of the most direct, or the most direct measure that the NOAA has on their website. So they have this El Nino and this ENSO dashboard where they have dozens of time series, different ways of measuring the ENSO phenomenon. And they have charts that look like this with red and blue splotches alternating. The most direct measure they have of the heat content deposited into the atmosphere in the tropics, in the tropical Pacific, or that's put into the oceans, is the heat content measure, which is essentially just tropical Pacific integrated temperature anomalies over a certain region of the tropical Pacific. And NOAA calculates this directly from a certain data set that they have. And so in the future, I intend to do some correlational analyses using this data set, but I would like to just put it up here so that you can see how it correlates with the UAH satellite temperature trend. I think it looks actually like a more accurate or reliable correlator or measure of how ENSO affects global warming. In particular, if we go back to the 2015-16 period, after this Super El Nino period here, in the heat content measure, we see the rise in temperature anomaly, and then we see a dip due to these La Nina events, and then another El Nino event here, which is followed by another rise in the temperature index, the temperature anomaly measurements, and then again a dip due to La Ninas, which corresponds to this dip, again with the around 6 months lag. And then again, we see another El Nino here, which broadly coincides with this rise in the temperature anomaly record. Of course, there's more going on here, as I think we suspect, because of Tonga eruption that released a lot of stratospheric water vapor. and very probably enhance the global warming effect from the El Nino event here. So yeah, this is a preview of future work that I will do. And well, I've already done some of it, and I think it does better describe temperature anomalies. Yes, David.
The 2016 temperature rise in the top graph looks small to me here
Hmm.
because we understand that it was much bigger than the 2023 El Nino,
Hmm.
but it doesn't seem
Well,
that way here.
yeah, so it's the magnitude of it also depends on how we're measuring it. So if we look at the oceanic Nino index or perhaps the MEI variable, then indeed it'll look like it's a much bigger phenomenon compared to later El Ninos or earlier El Ninos. Um, but as far as direct measures of heat content in the tropical Pacific, it turns out that those direct measurements show that it is still larger than the later El Ninos, slightly, but not by very much. The largest, it turns out, is the 97, 98 El Nino. So it's a question also of which metric is used or which metric we look at to measure the magnitude of the El Nino. Remember that MEI incorporates many, many different factors to quantify an El Nino event, whereas this metric is just looking at heat content as described, as defined as integrated temperature anomalies 160 degrees east to 0 degrees west in the tropical Pacific from 0 to 300 meters. So it is a more limited or restrictive measure or estimate of the El Nino phenomenon. Good. So just to wrap up now, I've provided 4 lines of evidence that, in my view, strongly suggests that ENSO is the dominant, or at least the most direct driver of global warming trends in the atmosphere, whether measured in the lower atmosphere, the troposphere, lower troposphere, or as measured by surface temperature measurements. And I say proximate because the ENSO phenomenon also is significantly influenced by other natural climate phenomena, such as the Pacific Decadal Oscillation, which is a much larger ocean atmospheric coupled phenomenon that overlaps with the region of the tropical Pacific where the ENSO phenomenon happens and can enhance ENSO or diminish it, depending on whether or not the phases match or disagree. Also, planetary albedo, or how much sunlight, for example, the surface of the planet or the atmosphere reflects back into space versus absorbs. Solar activity can also affect the ENSO phenomenon, and submarine volcanoes, which are not well understood or well mapped. The amount of the activity, the distribution of such volcanoes, that can certainly impact the strength and intensity, the strength and frequency of El Nino events versus La Ninas, and of course, many, many other variables. So it's an open question to understand what exactly are the factors that cause ENSO events to be of a certain magnitude as opposed to another? What explains the multi-decade cycles of the ENSO phenomenon, and so on and so forth? And so if ENSO is significantly impacted by all these other variables, then in a sense, global warming is also causally influenced by all these variables. But the primary driver, the proximate driver, would still be ENSO. And so more research is needed to really understand the variations in the ENSO phenomenon, and I think to better quantify its correlation with temperature anomaly records and such. But I think it is the most promising research line, at least as I've seen up to this point. So with that, I thank you for your attention, and I'm happy to take your questions.
Great. Thank you so much, Max. Awesome. I want to let Here, let me well, first, while you've got your screen share, do you have a chart of PDO to show or not?
Oh,
Not
not offhand. I don't
okay.
have off,
Yeah.
but it does. Well, what I can do is go back to an earlier map that I showed here. And so PDO is going to involve a much larger region like this. And there can be phases where, say, PDO is, it has a warm phase where it's releasing heat here and a cooling phase here. And so PDO can amplify an El Nino event, or if a La Nina event is happening here and PDO is in a phase where it's cooling here, then it can uh, amplify a La Nina event. So
Yeah, it'd be
PDO is
interesting.
occurring on the, yeah,
I'm sure you've seen it and you have it. I just would like to see the time series.
definitely.
Why don't you stop sharing now so we can just have a
Sure,
conversation then, unless we really need to share again. And let
sure
me
thing.
start by asking you to tell the group a bit about your background and what you currently do these days professionally.
Sure. Well, I am a theoretical physicist by formal training and current practice. I have a PhD in theoretical physics from the University of Utrecht. And so my main research is quite far removed from climate science. It's primarily on topics related to quantum mechanics and general relativity theory, foundational problems in both approaches, problems with how they might be combined together into a coherent framework of quantum gravitational physics, things of that sort. So that's my main line of work. I also have some interest in philosophy of science, and I've done some work in that area as well, logic and epistemology. But my main area of research is in theoretical physics. And so I got into climate science in a sort of unexpected and indirect way. Essentially, I was a few years ago knee deep in the literature of the economist Milton Friedman, who's one of my all-time favorite economists. And I was curious what Friedman would say about how to address global warming and climate change. And I thought that he'd probably say something along the lines of, oh, we should just have a Pigovian tax, or in other words, a pollution tax,
Right.
where CO2 is the pollution, and we should just tax it to diminish, to disincentivize uh,
Right.
CO2 emissions and fossil fuel usage. But I was struck by the fact that he never discussed the issue in any of his talks or presentations or interviews over the years, and he died in 2006. So he was around for a long time. He was around even when,
Six or
the
eight?
issue became
Six? I thought it
six.
was eight.
Yeah, just he died just before the housing bubble burst and
Okay.
the economic recession and all of that. He just missed all of that,
Yeah.
unfortunately.
Right.
But he never talked about this issue, and I was curious about that. So I did a bit more digging, and I found that there is one place where he's commented on the issue, and it turns out he actually wrote a short blurb endorsing a book by an economist at the Hoover Institution named Thomas Gale Moore. And Moore wrote this book called Climate of Fear: Why We Shouldn't Worry About Global Warming in around 1998 or so. It was published by Cato University Press. And he marshals very interesting historical anthropological evidence suggesting that earlier periods of the Earth, which were significantly warmer than today, at least in the northern hemisphere, in particular the Holocene climatic optimum period, shows substantial evidence that global warming, even if it's caused by man-made CO2 emissions, although he doesn't endorse that view, he just says even if it is caused by that, or really whatever is the cause, um, warmer temperatures are actually better for humans, or seem to be better for human well-being on average. And so whatever is causing the warming, we should be welcoming it and shouldn't try to reduce CO2 emissions at all. And Friedman endorsed this book glowingly, and I was very surprised and impressed or curious about that. So I read the book carefully, and I was very impressed with Gail Moore's arguments and evidence, and that changed my views. And he referenced a lot of the work of other people like Christie and Spencer and Richard Linton and other researchers who are now considered climate skeptics or climate realists. And so that's how I got into this area. And currently, I'm also still a researcher, postdoctoral researcher affiliated with Rutgers University. And I'm also a professional member of the CO2 Coalition and doing some consulting work from time to time for some private firms related to climate science.
And what do you think Feynman would have said?
That's a good question, too. And I would like to think that Feynman would not buy into these standard explanations and that he would be fairly skeptical, or he would see through the simplistic picture that I think tends to trick a lot of physicists or physics trained people. A lot of physicists and physics trained people have this very naive image of global warming as, oh, it's basically like having some sort of glass box with CO2, some portion of it's CO2. And if you increase the CO2 concentration and you shine infrared light into it, it gets warmer and warmer and warmer because the CO2 traps the light,
Right.
traps heat.
Right.
That's the simplistic picture they have in mind. They say, oh, it's just quantum mechanics. It's very simple. But of course, it's not really that simple. That's something that a physicist says who has never really studied
Right.
fluid mechanics, nonlinear dynamical systems in any serious way, or atmospheric physics in any remotely serious way. And I would like to think Feynman was careful enough of a thinker that he would not fall into that trap. But I don't.
Well,
I don't really
well,
know.
his sister was a solar scientist.
Hmm.
So I have asked his Joan's
Hmm.
husband, who's still around, what
Hmm.
she thought, and he said it was out of scope for her. She never said or mentioned anything about it. I've
I see.
asked Feynman's friends who are still around, and they've said it wasn't anything they ever heard anything
Hmm.
about.
That's interesting. There are some quotes of Feynman's about why government tend to screw things up or they cannot be
Right,
trusted with science projects, which
right.
makes me think he was probably a conservative of some sort politically. And he might be skeptical of data sets from NASA and NOAA regarding global surface temperature anomalies and things of that
No,
sort.
I'm a
But
Feynman expert. I don't think he was
mhm,
political at all. And of course,
no.
he worked on the Challenger disaster, and so he did a
Mm,
lot of he spent a lot of time at NASA and realized that it was a management problem. It wasn't an engineering problem. Let me just ask
I
quickly,
see.
any idea about Carl Sagan, who kind of
Hmm.
bought the whole story, hook, line, and sinker?
Yeah. Yeah, I think Sagan is a disappointment as far as that goes. There's this video of him giving a congressional testimony in front of Al Gore and some other U.S. Congressmen, and he's simply just repeating the naive story that I mentioned earlier as to why we should expect temperature anomalies to go up in the near future because of rising CO2 emissions, and it's something that we have to urgently avoid. And he likened the greenhouse effect on Earth to Venus, the temperatures of Venus and the concentrations of methane there, and CO2, and it's very, very poorly reasoned, and yeah, quite surprising to me. But maybe I shouldn't be too surprised. I don't know.
Well, he was famous for his bullshit detector, so I'm surprised. I'm disappointed that who knows when he would ever have retracted that. That's an unknown.
Yeah, I mean, some people have changed their minds over the years, I suppose. So I guess it's possible. I think Will Happer changed his mind at some point.
Oh,
I don't, other people have. Michael Crichton. I mean, he wasn't a physicist, but he was at one point a believer in the issue, and then he examined data for himself, and then he changed his views on that, and he wrote this book, Climate of Fear.
Right.
Not Climate of Fear, State of Fear, where he
State of fear. Right.
goes into that. And yeah,
Right. And a beautiful essay called "Are Aliens Called Cause Climate Change?"
right.
Let me open it up to the students. Corin, you got to unmute. Unmute, Corin. We can't hear you.
Unmute. Okay. Hello. Can you hear me?
Yes.
Yes.
Okay. Thank you very much for such an excellent talk. I hope you get invited to the Climate Change Committee in Parliament here. But the question I want to ask is very general. Are there I know the Rat Pack data goes back to the 50s. Are there, and it's not a criticism, I just want to know, because some people are not above using graphs for funny purposes. Do any of the graphs of the El Niñas go back before 1979?
Oh, yes. In fact, the graphs that I showed earlier of MEI, the multivariate Enzo index, they date back to as early as, or at least one of them dates back to as early as 1949.
Oh,
And
right, okay.
there are even metrics of measures of El Nino southern oscillation that go back to supposedly to the 1800s, late 1800s. NOAA has these time series on their El Nino, their Enzo dashboard, it's called. And so they're all
Okay.
publicly available. And they have some that go back to 1948 and then even earlier to the late 1800s. I'm not quite sure how reliable that data is, though. I suspect there's a lot of inaccuracy, but at least the data is there, however incomplete.
Okay, thank you very much. I'll have a bit of a look, and as you say, I mean, in 1800 they were sticking, a thermometer in the water off a sailing boat. So who knows?
Yeah, right.
Yeah.
Yeah. Well, thank you for your question.
So thank you for your talk.
Thank you.
Who else? Anybody? Les.
Max, it's very impressive stuff, and I fully understand. I think the relationship between the MEI,
Yes.
MEI and temperature seems very clear. In terms of fluctuations, the relationship in the longer term seems not quite so clear. It's quite hard for a layman to see that fully. But a broader question for you: what is the response of the climate alarmists to this sort of work, which is showing the link between Enzo and temperature? Are they dismissive? Are they even acknowledging this work?
So the response has generally been dismissive, at least from some subset of climate scientists who have discussed these arguments. In particular, the first charts that I showed from that paper in 2009 by McLean and Freitas and collaborators, that paper, although it was published in the journal that I mentioned earlier, after publication, a number of climate scientists wrote into the publication and condemned the publication of this paper. And there was a response to the paper, and then the authors wanted to respond back, but they're to critics, but the journal did not allow them to publish their response to critics. So that seems to be a fairly negative critique. I have read at least one of the publications critiquing that paper, and the authors on it, the lead authors, are some of the usual suspects like Jim Hansen and Gavin Schmidt, among others. And I frankly didn't think that their criticisms were particularly relevant or substantive. But you just have to take my word for that, or perhaps read the criticism for yourself and see. So I wasn't particularly impressed by that. And as far as the other work, there really hasn't been much direct response to, say, the Wallace DeLeo Christie report that I discussed last, or Spencer's blog. One thing that climate modelers do when they try to account for the impacts of El Nino Southern Oscillation, and they say, oh, this is sufficient, is they simply see ENSO as producing warming on a monthly scale, and that's it. So they don't look at the cumulative impact, or they don't model the cumulative impact of the ENSO phenomenon. But I think physically that's a mistake, because if you have this ocean atmospheric cycle in which heat is being transferred from the ocean to the atmosphere and vice versa, well, you have to, if you want to analyze the cumulative impact on global average temperature anomalies, look at how the net heat content of, say, the atmosphere changes over time. And the way you do that is by a cumulative measure. So summing the values, say, of the multivariate ENSO index over time, or the heat content index over time. And surprisingly, the climate models don't consider that, though the CMIP5, CMIP6 models that the UN IPCC report relies on. And other modelers like Gavin Schmidt and others, they don't seem to consider that either. So as far as I can see, they just don't really try to seriously analyze or model the global warming impact cumulatively over time of the ENSO phenomenon. They just make this very incomplete, naive analysis, and they leave it at that.
On a different question, you're at a university, you're a scientist there. You haven't published, I think, this work, but you've made it publicly available.
Right.
What's the response you get from those around you? Are you because universities are not generally in the same place that you are?
Yeah. Well, mostly it's, well, I've pursued essentially this policy of don't ask, don't tell. So if I don't need to, if they don't come across my work, I'm not going to mention it to them. But if they come across my presentations on YouTube, say, at some point, and then they want to bring it up, then I'll be ready and happy to talk to them about it and say what I really think. But mostly it's through private conversations on social media with colleagues that have discussed this issue, and mostly the response has been negative or skeptical. But opinions sort of vary. I do have some colleagues who agree that global warming, they're convinced that man-made CO2 emissions are the primary cause of global warming, or at least they take that for granted. And they're convinced that there is this overwhelming scientific consensus and all of that. But they agree that it's not the end of the world, and they tend to be favorable to something like a CO2 tax or something like that. But it's not been something that's overtly negatively impacted my career or reputation, at least not yet. So who knows in the future? But I think, for me, it's such an obvious, the entire climate change agenda, so to speak, is such an obvious scam that the alleged consensus is so obviously fake and manufactured that it violates my dignity to just quietly go along with that. And I think my colleagues, especially those who work in the foundations of quantum mechanics and quantum physics and see themselves as somehow special purveyors of scientific truth, that they should apply that sort of, well, they see themselves as people whose goal is to clarify the physics community's understanding about foundational issues in quantum mechanics related to the measurement problem, the relevance of observers to quantum measurements, and things of that sort. But they don't really apply that same sort of, I don't know, independence of thought, I suppose, to this other issue. Overwhelmingly, they're all Democrats,
Right.
left-wing Democrats politically. And so I think whatever rigor of thought and research they do within their scientific work, it seems to go out the window when it comes to a politicized issue like this one, which I've still not fully understood. But yeah.
Okay, Corin.
Okay, sorry. To show my ignorance again, is infrared radiation, is that the same as long wave radiation?
That's what's meant by long wave. It's
Okay.
infrared, so heat.
Okay, and will the excellent Liz Avramedes be talking about that next week about long wave radiation on CO2?
Yes, she will be.
She will be.
Oh,
Okay,
nice.
thank you very much. Thank you, Liz.
Nice.
Any other questions?
Yeah,
Liz, please.
yeah. So thank you, Max. That's really helped me to understand ENSO much more than I ever did before. If the ENSO phenomenon is accounting for all the temperature rise, that means, as you implied in your slide, that all the other things like increasing or decreasing solar activity will feed into that phenomena, and that is what is going to be the manifestation of all those other influences. So is there a lot of research being done on the interaction between all the different possible influences?
There is some research done on this, but overwhelmingly, the research that I've seen done on ENSO today concerns or focuses on the impact of man-made CO2 emissions on the frequency and intensity of El Niños and La Niñas, and also the impact of aerosols, man-made aerosols, on the ENSO phenomenon. So you can find a number of papers published in Nature where climate scientists write these computer models, these very simplistic models of the ENSO phenomenon, and they try to argue that rising man-made CO2 emissions can probably increase the frequency and intensity of El Niños. And that's another way that man-made CO2 can enhance global warming by enhancing El Nino, for example. But in terms of the other things that I mentioned, the relationship between the PDO and the ENSO phenomenon, that is the Pacific Decadal Oscillation, and the ENSO phenomenon, or the relationship between ENSO and solar activity or undersea volcanic activity. There is some research being done on that from what I've seen, but it's definitely not at the forefront, and certainly not in the the media's attention.
Yeah.
So I agree there should be more work done on that.
That's strange because, as I understand it, the ENSO is more to do with the heat exchange between the surface and the deep ocean, rather than being influenced by the atmosphere. Is that correct?
Well,
very oversimplified interpretation.
Well, keep in mind that it's dependent in large part on these trade winds between Tahiti and Darwin and how strong they are, or whether or not they weaken or reverse. Now, what can affect the trade winds? One thing that can affect it is air temperature, say, as a result of, let's say if air temperature goes up because solar activity increases, so the solar radiation output of the sun goes up. And let's say there's less low-level cloud activity, so that there's less sunlight reflected back into space. Then the air temperature near the surface of the ocean in the tropical Pacific will be higher, and that will presumably affect the trade winds, like, for example, weakening them or reversing them. And then that could enhance the El Nino phenomenon. Or if cloudiness over the tropics goes up for some reason, then that can also impact the trade winds. because then it gets colder, the air temperature gets colder, and that strengthens perhaps the trade winds, and then you get more La Nina events, for example. So part of it is deep ocean, but also surface too, surface ocean phenomena due to the trade winds. So it's both. And so that's why, for example, the submarine volcanic activity could also potentially, affect it. If there's a lot of volcanic activity in the deep ocean and then that heat bubbles up to the surface in the tropics, then yeah, that'll have an effect.
Tony.
Hi. I noticed that there was good correlation in the later graphs that you showed between ENSO and the air temperature measurements. But the earlier graph of the modified, or the version 2 of the multivariate ENSO index from 2020, 2023, I think there was a small or it seemed to be a small El Nino and a large La Nina present there, but the average temperatures, or the some temperature measurement that it was compared to, remained high, and I just wondered whether pivot in 2019, whatever has gone into that, designed to show less correlation with temperature from 2019. I don't know. There was just some question in my mind as to the veracity of that change at 2019.
So if I can, I'll just briefly share the screen of the chart that you're referring to. I'm assuming you are referring to this chart?
No, that's the later one. He means
This is the later.
MEI2.
The MEI2?
Yeah, I
Is,
think.
yeah.
Yeah.
Good. So this one.
Yeah.
So in 2019, there are these tiny El Niños, and in 2019, temperatures start to go up around between 2019 and 2020. And then they come down again. And that coincides with these La Niñas.
Yeah, I thought that there would be a larger downturn in temperature.
Yeah. Because of these large La Niñas. Yeah. So this goes back to what David and I were talking about earlier regarding the change in the differences between the multivariate ENSO index version 2 and the multivariate ENSO index version 1. Unfortunately, so in general, the MEI, the original MEI, shows that on average, El Niños are larger in magnitude than seen here in the version 2, and that La Niñas are smaller in magnitude, or have been smaller in magnitude since 1979 than shown here in version 2. Unfortunately, the MEI was discontinued after 2018. So we don't have MEI data for 2019 and post to compare to this. But if the past data set is any indication, if MEI were continued on to today, the magnitude and perhaps the frequency of these La Niñas would be significantly less than what's shown here. So because of the difficulties and the complications of MEI versus MEI version 2 in recent years, that's why I have looked for a recent measure that's also more direct and kind of evades all of that. And so it seems to me that the heat content metric here is a better indicator of things, perhaps, because, well, yeah.
Yeah, I agree. I agree with that.
It just seems to better describe things.
I have a question,
Mhm.
Max.
Yes. And
Here,
I'll
let's,
stop sharing this.
yes, there we go.
Yeah.
Yeah.
Yes.
So, how does this all affect global ocean currents? If we look at the Southern Ocean, and then how does it affect anything in the Atlantic on our side of the pond? With the Gulf Stream, the direction of how the Gulf Stream works, or what impact does this have? Or that's my question on global currents.
Well, I don't know the exact answer to that, but I would say that I'd expect it to have some impact, simply because if the majority of global warming since 1980 has been caused by El Niños, then it's been a global influence. And one thing we do know is that temperature anomalies in the global average temperature anomalies in the northern hemisphere have been significantly more positive or larger than in the southern hemisphere. Most of the global warming since 1980, as indicated by the satellite data, has been predominantly in the northern hemisphere, and pretty much like all of the northern hemisphere, and especially the more north you go. So if that's being primarily caused by ENSO, or if the heat released into the atmosphere by El Niños is migrating north for some reason more so than south, then that should have some impact on other ocean currents, and like the AMO, for example, and the Gulf Stream. But the exact details of that, I suppose, whatever people say that global warming in the northern hemisphere, however that's affecting these other ocean currents, that would be the way in which ENSO is affecting them, if ENSO is the primary cause of global warming in the northern hemisphere.
Okay, all right. And I disagree with Colin about in the 1800s, they were chucking thermometers off the side of sailing boats. They were excellent at recording stuff back in those days. Captain Cook in particular. So the records, and I think mercury measurements are pretty sort of standardized and accurate.
Do you think the regularity of measurements was also as good as, or good enough? So the consistency or the frequency with which measurements were done back in those times? And the reason I ask is because, for example, in NOAA's data sets that they use to map changes in the global average temperature anomaly of the oceans, there is a lot of spottiness and irregularity. And they get their data from this other database called the ICOADS database, which is using buoys and ships and measurements from ships in different parts of the oceans. But there's a lot of spottiness and incompleteness in that data from what I've seen when I've looked into the actual raw data. And at least, especially the further back you go in time. Now, maybe that's just NOAA's data that's problematic, and maybe it doesn't apply, say, to I don't know, sailors and oceanographers in the 1800s or so. Maybe they were more consistent. But do you have any ideas about that?
I don't, to be fair, but I should imagine the Royal Society have like very accurate records of it all, because they were the sponsors of Captain Cook's expeditions, and everything was recorded and as accurately as possible. And if they could chart out the Pacific Ocean so accurately back then, I'm sure they would be quite good at like measuring the temperature of the water when it was on the way as well.
Michael, Andy May has written a bunch about this, and so
Okay.
I can point you to some of his work on that.
Okay, thank you anyway. Great presentation.
Thank you. Thank you for your question too.
Corin, I'm gonna draw the line here because we've kept our guest Max here for more than an hour and a half, and I have 27 questions, and so we're not going to get to all of them. I really appreciate it. I want to ask you one question, Max, because
Yes.
and I'd
Yes.
love to have you back to tell us about quantum gravity and dark energy because I'm fascinated by these things. But I'm it's maybe
Sure.
I may fill our time in March or April with some physics. We'll see.
Sure. It's fun.
My question is, my lectures for this class are almost all based on Javier Vinos's work.
Mhm.
I assume you've read at least his work, his chapters on El Nino and PDO AMO stuff, or I don't know if you have.
I know he has this recent book. I have not read
Okay.
his recent
So
book.
the basic idea is that a huge amount of energy goes into the oceans through
Mhm.
shortwave radiation, and then is 20% of all the incoming energy coming to the Earth moves from the tropics out to the poles and exits through the
Mhm.
poles. So his big hypothesis has to do with meridional transport of heat. And the only way that happens, the obvious way that happens, and I don't know if I'm going to get the directions right because I know it's backward for you, but sunlight coming in, and we can use the Pacific. Where is the Pacific? I don't know. Sunlight coming in. I've lost it. See, it's backwards for me, you guys, so it's hard for me to hear.
Mhm.
Sunlight comes in, and then it makes its way from the Coriolis effect west. Right? And this is true in all ocean basins.
Okay.
Right? It's going because the
Mhm.
Earth is turning east, and
Mhm.
so a tremendous amount of heat
Mhm.
moves west, where at some point it hits something, and then it's diverted some of it north and some of it south, and a tremendous amount of heat goes to the poles and is emitted to the poles. This is what we call the heat pump in this class.
Mhm.
All right, and it
Mhm.
happens in both the Pacific and the Atlantic.
Mhm.
So at all times, a huge amount of heat is entering the system and leaving. And
Okay.
all right, and so
Mhm.
in that context, because it's happening in a in the Pacific, probably more than the Atlantic, just because the amount of heat being gathered here is the way he frames it is that the El Nino is the release of built up heat, that when it gets to a certain threshold, and this is why it's hard to predict, it's not regular, but when the conditions are right, that enough heat has built up, then it will cause this release. And that's just a natural valve for moving heat then through the atmosphere and through the various currents that take it north and south. And that gives you this reaction, which you know all about the pressure systems and the deep water coming up and so forth. And that it's really more of a stochastic event after a certain amount of heat has built up and then causes a reaction, just in the same way that clouds will form when temperatures get to 30 degrees, in the tropics. That causes clouds. They can't go higher than that. It's a reaction. And so in that sense, it's not a battery cycling back and forth and back and forth and back and forth. It's a battery storing and releasing.
Mhm.
And releasing out to away, to the Indian Ocean dipole, to the whatever current, and through the atmosphere up to cause our snowfall and everything else, our El Nino. And, as you show, has a huge influence around the world. So do you think of it in terms of that much heat coming into the system and leaving and getting released, built up and released periodically?
Well, there's definitely an accumulation of a buildup of heat content um, in the oceans, that then gets released into the atmosphere in some way. So that does, how does he think about La Ninas, or how does that factor into his explanatory
Yeah, if
framework?
you read his chapter on this, he says that the La Ninas, and he's big on the neutrals. For him, the neutrals are in a zone that's fairly wide. I don't know if it's half a degree either way or 1 degree, but there's a lot of neutrals in his, if you
Okay.
read his chapter. So what he says is the La Ninas and the neutrals have a pretty regular cycle, and the El Ninos punctuate it through the release of a built up heat. And so that there's this kind of underlying cycle of La Ninas and neutrals. And he's got some papers that he cites on this. And I think that's possibly why he also talks about the lunar, the tidal effect as well. But it's very hard to predict, especially the size of an El Nino, because you'd have to be watching the buildup of heat that particular cycle, or not cycle, but at that particular, it's a phenomenon, it's something that is triggered when so if there were more clouds or less clouds, that would build up heat in the
Right.
system, and at some point it would get triggered and it would be released on top of the El Nino neutral cycle.
Okay. That sounds like it's broadly, mostly compatible with my understanding of the phenomenon, and I'll have to read his chapters from his recent book to, I guess,
You
learn about
should, and
more about that.
he claims that he correctly predicted the 2023 El Nino and more or less its magnitude, but I haven't read how he did that. It was in our email that we exchanged with him,
Oh, I see.
and he's
Does
sort of on record. He's on record predicting it a couple of years in advance.
Can he do any sort of retrodiction of past El Ninos based on, I don't know, whatever data sets are available, like going back to like the 1980s, and then see how that compares to, say, MEI or MEI version 2?
I can't answer that. I think he does a lot of principal component analysis stuff. He's always looking for, underlying signals that may be hard to see if you look at everything combined. So I encourage you to read his chapter. You probably have it, but I can send you the PDF if you want, or the link to the PDF. And then, have a look at it. It's pretty detailed, and I just wonder if you actually, I'll do it by email and then I'll report back to the group. We'll see if when you have time to read that chapter, then, I'll report back to the group what you say, your response.
Yeah. Yeah, I'd be happy to read it, give it a read. I don't remember if I have his book. Is his book available for free, or
It's
is
a
it
free PDF, or
free
you can
PDF?
pay to have it printed. It's a beautifully printed book, but you're gonna have to pay about
Okay.
$80 to get the printed version.
Gotcha. So yeah, if you could send me the
Sure.
PDF by email, that would be great.
Sure. Yeah. Well, that's our textbook for the class. So I am,
Oh, okay.
I am kind of interested
Great.
in if that changes your view at all, because what we see as a class, because we've been through this, is huge amount of heat moving through the system, and then the El Nino is just this kind of wave that comes up, every so often because of that transfer of heat that's all driven by the sun, right? It's all solar energy coming through. And it's not much of a back and forth oscillation, from Darwin to Tahiti. It's, in other words, it sloshes through east to west, and then there's kind of a back, west to east backfill, which is part of the phenomenon, and that moves a lot of cold water up and so forth. But the driver is the east to west flow of hot water.
Okay. Does he comment on or talk about the impact of Enzo and his understanding on global average temperature anomaly measurements and
He does, but he's also a big AMO fan, as am I. So, you know, another question I'm not going to post, I'm not going to get an answer from you today because I want to wrap it up. But, you know, if we had somebody who's a big proponent of the AMO along with you, you know, and talk and trying to sort it out, you know, we would probably find common drivers. We'd probably find interactions. We'd probably find a lot of complex, you know, maybe at some points the AMO is more dominant or something, and that, you know, because AMO has a huge effect. You could give a similar talk to the one you've just given for AMO, and it has a very strong correlation. So, like, you know, what are the underlying drivers? Right.
Okay.
And there's no, we're not trying to answer this here, but that if you're to answer to your question is he would say that the AMO is probably just as predictive or as causative in some way. And so the question then becomes, okay, what are the things that cause both?
Right.
Because
just
according to him,
cause.
you know, according to him, you know, the heat builds up along the oceans and all works its way west all the time in every ocean basin. And that all gets driven, that energy gets driven into the air and into the currents that then flow poleward. And all of that activity is what creates the global average temperature.
Okay. Oh,
so we'll ask you to have a
I'll
look
have to
at his book.
take a look.
and
And I would be very interested if did you have references to recommend on AMO's correlation with temperature anomaly
his chapter. Yeah,
records as
look at his
well?
chapter because he's referencing published literature, and he's got a lot on it. So you'll see it in there.
Okay.
Yeah.
Great.
Okay.
Yeah.
Thank you so much for taking the time to talk with us.
Well, thank you for inviting me, and thanks to everyone for the questions and for listening, and enjoyed the conversation.
You think about interesting things, Max. We'd love to have you back and just continue talking science. That's always something we enjoy.
Thank you. Yeah, I'd be happy to talk about physics topics, other topics too. So.
But we'll see if everybody's interested. We'll take a vote. I vote. Okay. All right.
Good.
Thank you, everybody. This will be recorded for our community. And next week we have Liz telling us about radiative transfer. So we'll see you next week.
Great.
Thank you. Okay.
Take care.